Okay, so my plan is to tell you what KSBA moduli spaces are, and then I will talk about KSBA moduli spaces for toric varieties and then for low Calabi-Yau surfaces. So I'm mainly a log geometer, but I like using log geometry in different ways. So in the last couple of years, we figured that log geometry is useful to understand moduli spaces. And to start to tell you about moduli spaces, I want to mention, you might know the Lee-Mumford moduli spaces of stable curves in Bargian is one of the most extensively studied objects in algebraic geometry. So this is a moduli space consisting, if you fix some integers gn, then if you look at all pairs C, P1 to Pn, where C is a reduced algebraic curve of arithmetic genus G, and these are marked points on C on the smooth locus, and we want C to have only adverse nodal singularities. On top, we want to ensure that the automorphism group of such a curve with marked points is finite, which is equivalent to saying the canonical divisor summed up with the divisor of all points is ample. One can check that this condition of requiring this divisor to be ample ensures that the automorphism group is finite. So this is a nice moduli space shown by the Lee-Mumford. It's a nice algebraic stack. It's the Lee-Mumford stack. One can calculate its dimension, and it has been extensively studied. So theorem, this moduli space is a DM stack. It's due to the Lee-Mumford interval. And KSBA moduli space is going to be a generalization of the moduli space of stable curves of the Lee-Mumford to higher dimensional algebraic varieties. It's actually a generalization of Lozef-Monin and Hosset, who introduced a version of the moduli space of stable curves. They defined the weighted moduli space of stable curves. So in the work of Lozef-Monin, when you look at Lozef-Monin spaces, which is generalized by Hosset, you look at points together with the data of some associated weights, which are rational numbers. And I will tell you a generalization of this, where you consider, in addition, some weights. So I will define it in generality now, where you work with moduli spaces of higher dimensional algebraic surfaces, where you have also associated weights. So this was defined by Kollár-Shepherd-Barron and Alexeev. To define this moduli space, again, similarly to the data we fixed here, we need to fix some numbers. So fix D and some weights, which are all rational numbers, such that each of them is between 0 and 1, and I fix another rational number, V. And once I fix the data, I can define the moduli space of Kollár-Shepherd-Barron Alexeev. It will be consisting of all pairs YB, where Y is a projective variety of dimension D, and B is a Q divisor in Y. such that it has a decomposition into BIs, divisors. You can write it as the union of, as the sum of divisors, where the weights appear as coefficients. And I, again, analogously to the moduli space of stable curves, I want some conditions on such pairs. So I want mainly two conditions. I want YB to have semi-log canonical singularities. So these type of singularities are extensively studied in birational geometry, especially people doing minimal model program. You can think of it a natural generalization to higher dimensions of what a nodal singularity for curves is. And furthermore, I want, again, the canonical divisor of y plus b, similarly to the stability condition I had above. I want this to be ample. And if I do not put any further condition, I would get infinitely many components of this moduli space. I also have the state of V, so which I will use to also fix the volume of YB, which by definition is the self-intersection number of ky plus b with itself d times. I want it to be equal to some fixed number to ensure that I will end up with finitely many components. So here, one can check that if you choose all of your weights to be equal to 1, and if d is equal to 1, and all your weights to be equal to 1, then fixing the volume will amount to fixing 2g minus 2 plus n, so it will fix the genus. Then this moduli space will just agree with the usual Deligne-Mumford moduli space of stable curves. Okay, and if you fix d to be 1 but vary the weights, it will agree with the Lozif-Manin or Hasid moduli spaces. It's a theorem of many people over several years that this moduli space, starting from Kollár-Shepherd-Barron, Alexeev in dimension 2, that this moduli space is also a proper Deligne-Mumford stack. However, unlike in the situation for curves, the connected components of this moduli space are not generally irreducible. And one of the main questions people working in this area are interested in answering is, what is the geometry of connected components? Or what is the geometry of irreducible components in this moduli space? And this was first answered by Alexeev around 20 years ago, when you look at the situation when you're interested in toric varieties. So I will first tell you the known result when you consider toric varieties, and then I will tell you what we did to understand this moduli space for surfaces. So in the toric case, I fix a toric variety y, and d, I let d to be the toric boundary divisor, which by definition is a union of, is an anti-canonical divisor given by the union of all divisors which are fixed under the torus action. So there is a C star to n action on toric varieties. And I consider also a polarization line bundle given by an ample line bundle on y, And you can encode this data. The nice thing about toric geometry is everything is combinatorial. You can encode this data and the image of the momentum map associated to YDL. So if you look at this polytope, which will be the simplest non-trivial example, which you can see if you have the original edition of the book of Gelfand, Kapranov, Zelevinsky. This polytope will define a singular pixel surface, dp4 of degree 4 as a toric variety, together with an anti-canonical polarization. As you take a lattice polytope, if you have only one interior integral point, the polarization will correspond to the canonical one. Okay, so I will use this as an example to tell you more things about the situation. So in this toric case, I will define the reducible component and the KSBA moduli space. By definition, this is a closure of the locus of all stable pairs deformation, all stable pairs that are deformation equivalent to y d plus epsilon c, where y is a toric variety, d is a toric boundary divisor, epsilon I take as a small number close to 0, and c is a curve in the linear system of L. So I want to particularly study these tuples when I look at the toric case, where my b here is given by d plus epsilon c. And one reason is that in the KSBA moduli space, there are two main conditions you need to check to be in the KSBA moduli space. When you sum up the canonical divisor with b, you want it to be ample, and if you choose b to be d plus epsilon c, because d is anti-canonical, you will only be left with epsilon c, which will automatically be ample, so this condition will be good. So in this moduli space, one can show that if you choose epsilon small enough to ensure the SLC condition that your pair has semi-low-canonical singularities, it suffices to ensure that C is transverse. So this is, one can check, this corresponds to the moduli space of all torically transverse C. Which means that if you look at your toric variety, I will draw its momentum polytope as before. There's the curve, I will just illustrate it. It's in the momentum polytope image. So you want C to avoid the zero-dimensional strata of the toric boundary. So that's what we mean by torically transverse. So in the toric situation, what we're looking is essentially the moduli space parameterizing all torically transverse curves. One can check this definition reduces to that. And it was shown by Valerie that this moduli space itself is a toric variety. If you want to be careful, it may not be normal. You may need to normalize. Is a toric variety. And he concretely described the combinatorics of the toric variety. He described the fan of it with fan, the secondary fan of P, whereby P, I denote the momentum point-up image associated to your YDL. And I will very briefly tell you what the secondary fun is, and then give you how the proof works, give you a rough idea on how the proof works. Okay. In the meantime, if you do have questions, comments, you're welcome to point out. I will tell you a generalization of this. So I started with the toric situation. So this moduli space, if you consider when y and t are toric variety, if you consider this moduli space, Valery showed that any irreducible component of this moduli space is a toric variety. And he described each irreducible component, the geometry of each irreducible component. And for toric varieties, you might sort of expect that, because toric varieties are so combinatorial, themselves are toric, you can expect roughly to get a moduli space which is also combinatorial, toric. But surprisingly, even when we do not consider toric varieties, our main result will show that for low Calabi-Yau surfaces which are not toric, we will still get toric varieties. So that's what we showed, and I will come there. So this was like in 2002, like more than 20 years ago. In the toric case, it was shown it's always toric. Do you have any other questions at this point? I'm coming there. In this definition of the moduli space, so so if you look at the original papers of Lozef, Manin, and which did this in genus 0 and Husset, which generalized it, they have this constraint, and they have further constraints on the weights. So they allow points to come together when the weights sum up to 1 and so on, and only under those situations they can show you actually get a proper Dely-Mumford stack. In this situation, when I choose my B to be D plus epsilon C, it's a good question, what are my weights actually? So D will be the toric boundary divisor. So D here will have 4 components, for instance. So this will be equal to D1 plus D2 plus D3 plus D4 plus epsilon C. So here, in this situation, what we fix is actually the weights to be 1, 1, 1, 1, 1 epsilon. So the weights here I'm fixing as 1, 1, 1, 1 epsilon. So in this problem, we are fixing the weights to be all ones and then epsilon for small epsilon. And it's crucial in this construction because when you look at modular spaces of surfaces, you want to understand all the generations of these surfaces, some space parameterizing them. And it's crucial in this deformation theory idea to be able to show that this modular space is equivalent to the autorically transverse C. You need to ensure that your epsilon is sufficiently small, whereas your weights are also between 0 and 1. They're both used.
And here epsilon is fixed or
right, so in this argument, it is shown that one can show that there is a stable range of epsilon. So there's a range for some very small epsilon. If you choose epsilon small that some certain number, this moduli space is going to be independent of epsilon. So there's some certain epsilon you can find, and below that epsilon, it's going to be independent. Good question. Okay, so I want to give you an idea of the proof how this works. I want to first tell you what is a secondary polytope. What is a secondary fan for P? There's a secondary fan and a secondary polytope. Similarly to in toric varieties, you have the momentum polytope and its dual fan. So let me just illustrate this on this example. Whenever you have a polytope P, you can associate to it the secondary fan, defined by Gelfand-Kapranov-Zelewinsky, GKZ fan. It's a fan whose maximal counts are in one-to-one correspondence with regular triangulations of P. And by regular triangulation, I will not go into details, but there is some height function. You can visualize this as some convex cell defined by some. So let me just illustrate this in this example. So if you take this diamond-shaped polytope, there are 3 triangulations. One of them will look like this, the other like this, and the other like this. So in this case, for this particular polytope, the associated secondary fan, which is some very well-known object, I see there are many tropical geometers here, is just a fan of PT. So Valerie's result will say that if you look at the KSBA moduli space for the singular del piezo surface, NYDL is going to be equal to PT. And let me give you an idea on why it is true that it is a toric variety. It's the secondary fan, yes. Gelfand-Kapranov-Zelewinsky fan. And I first saw the original book 3 years ago when I saw the book of Valerie. It's a very beautiful book with this picture on it. In the next editions, they removed the picture. So it's a pity because everything started, our whole project started with this picture. It's a complete toric fan, yes. And I will give you an alternative description on how to describe this fan using mirror symmetry, which will... This lattice of co-characters for the polytope, or right? So to define the secondary fan, this will be the dual lattice. Yes. It will actually be a bigger lattice. So the toric variety associated to the secondary fan is not going to always have the same dimension. So the secondary fan can have different dimensions. So for instance, if I choose a much bigger lattice polytope, the secondary fan will be much bigger. I will tell you what the dimension is. It's going to be the dimension of the toric variety associated to the secondary fan is going to be equal to the dimension of integral points in your original polytope minus dimension of y minus 1. So it's not immediately the dual lattice. It can be a different. So has to do with this construction that I skipped. You need to consider some data of heights and stuff. So let me give you an idea of why this is true. So whenever you have a toric variety, the nice thing about toric varieties, when you fix an ample line bundle, which defines to the point of P, the space of sections of this line bundle has a nice monomial basis given by, which is parameterized by all integral lattice points in your polytope. And what are used to is the fact that there's such a nice monomial basis. So if you look at any curve into an ample line bundle of L, you can write it as a sum of AI, AP, Z to P, where AP are some coefficients. And if you look at the situation where consider all curves C such that APs are elements in C star, then one can show that if you choose all your coefficients in C star, the condition that we are looking for, that this curve C is not going to pass through the zero-dimensional strata, are going to be torically transverse. If you choose all in C star. And then this already gives a torus, so if these torically transverse curves give a torus C star to the, as you were asking, the number of integral points in your polytope. Up to reparametrization, you need to subtract dimension y minus 1, so you will get this torus inside your KSBA moduli space. So by looking at all such curves, you can already see there's a torus inside your KSBA moduli space. It's not enough to conclude that you have a toric variety. You need to show, like there are many varieties which are containing a torus, but which are not toric varieties, like cluster varieties, for instance. So he still he used the properties of this nice basis to show that there's a natural compactification of this torus to a toric variety. And what he did to do that is to show that if you have any such torically transverse curve, then if you look at all the generations and the generations of your YDL, which one can describe by looking at the combinatorics of the secondary fun. So remember in this example, I told you P2 is a secondary fun for this polytope. So he studied all the generations of torically transverse curves and showed that they all degenerate into torically transverse curves in the secondary fun to conclude that this secondary fun giving you the toric variety is the correct toric variety compactifying this torus and giving you the KSBA moduli space. And to do that, he used properties of this monomial basis that exists in toric situations. So what we want to do, what we did, was to generalize this result to show that we get KSBA moduli spaces which are toric for things that are not toric varieties. And our idea is to find such nice bases for the space of sections. However, in our situation, when you no more have toric varieties, you no more have a secondary fun. So part of what we did is to find an alternative description of the secondary fun for P in terms of birational geometry. We showed one can rather study with the Mori fun of some threefold, which is the mirror family to YDL. And I will tell you first in the toric situation what the mirror family is, because we want to generalize this result of Valery to beyond toric cases. So we can no more have the notion of secondary fun, but we will have mirror symmetry and birational geometry, so we will use that to generalize this. Okay, in the toric case, again, the mirror is constructed, so toric geometry, mirror symmetry for toric geometry is rather well understood. It roughly suggests that if you have a toric variety, you can construct a mirror by exchanging the momentum polytope and fan pictures, as you were saying, which are living in the lattice of characters and co-characters. So in the toric case, if your P is this polytope, then you can construct, so I want to, because mirror symmetry has to do with families, I want to have one more dimension, so I want to consider the cone over this polytope, cone P, and I want to declare it. Mirror symmetry says that if this is some polytope picture for your original variety, you can understand the toric mirror by looking at the cone over P and view it as the fan of your mirror. So I want to view this as a fan for some threefold, let me call it X bar. However, in mirror symmetry, which is a phenomenon proposed by physicists, which roughly says that you can consider degenerations, complex degenerations on one side, the modular of complex structures should agree with the modular of Keel structures on the other side. So you always work with degenerations. And if you want to understand the mirror of a maximal degeneration of YDL, which we said is prescribed by taking a triangulation of this form, then the mirror in this case is going to be a Crépin resolution of this X bar, which I denote by X, which is now the toric variety whose fan is the cone over this picture, where you now also have additional cones where you take the cone over this picture. So X here is local P2. Sorry, local P1 times P1. So one can use basic toric geometry to check that if you want to get the data of the secondary fan, it suffices to study birational geometry of all Crépin resolutions of the singular thing, and this will give you a so-called Mori fan, and that will be equal to the secondary fan. So there is the work of Keel telling what the Mori fan is. So the Mori fan of X, this will be the same thing as the secondary fan of P if you have a toric variety. And to define the Mori fan, so what you need to do is to look at, so the maximal cones of the Mori fan, to define them, will be in one-to-one correspondence with the nav cones of all Crépin resolutions of your singular toric variety whose fan is the cone over this. So in this example, you have one total Crépin resolution. If you look at the nav cone of nav divisors, because you have local P1 times P1, its cone of nav divisors will just give you a two-dimensional fan. The nav cone of KP1 times P1 is the same as the nav cone of P1 times P1. So you might initially think, okay, I don't have a complete fan. So what you need to do is there's a construction of Keel saying there's a natural way to add bogus cones to complete it to a toric fan. So you will again get P2 as your Mori fan in this situation. And to define what the bogus cones are, all you need to know is all divisorial contractions in your original toric variety. You know that, so this KP1 cross P1 was the toric variety whose fan is a cone over this picture. You can apply a divisorial contraction. You can contract a P1 here to get another variety, another threefold, whose fan is the corner with this picture and the momentum thing, and the which appeared in the here. Okay. So if you look at these two triangulations, if you take the cons over these things, you will again get partial Crépin resolutions. Because you contract P1s, you apply the divisorial contraction, their Neff cones will have one dimension less. But then the construction of bogus cones tells you to add the divisor what you contract and to define bogus cones by studying all P1 times P1, all divisors that you contract. So there's some construction of the Mori fan using the data of just the birational geometry of X together with all the divisorial contractions. And while in the non-toric situation, we do not have the notion of a secondary fan, what we do is to use birational geometry to generalize the notion of the secondary fan by doing mirror symmetry and birational geometry. So I will state our main results and give you an idea on how we do that in the non-toric situation. Okay. Mori fan. So whenever you have a Mori dream space, which ensures that if you look at, say, X, if X is a Mori dream space, it's a nice space, which means you look at all possible Crépin resolutions of X, and you look at all possible Neff cones of them. And generally, if you do not have a Mori dream space, all this data of all possible Neff cones may not really, they might not be polyhedral, nor they may not be gluing together to a complete toric variety. But Keel said that for nice varieties X, you can glue together all the Neff cones of all possible Crépin resolutions of your singular variety. And then by adding some additional bogus cones, which he can describe combinatorially, he proved that all these built a complete toric fan. So the Mori fan is a fan whose maximal cones are the Neff cones of all possible Crépin resolutions of your singular variety. So generally, there's like big conjectures in birational geometry, like Kawamata, Morrison, and so on, saying that you cannot do this if you work with arbitrary varieties. But Keel introduced this Mori dream spaces where he ensured that you can look at all Crépin resolutions and their Neff cones glued together to a toric fan. Okay, so now the conjecture we proved has to do beyond the toric case, so non-toric case. We look at Y, a projective variety of any dimension. We don't necessarily assume it's smooth. And D, reduced anti-canonical divisor in Y. And we also want this to be maximal. We had this condition which amounts to saying that D has a zero-dimensional strata. So we don't want D to be smooth. It amounts in dimension 2 to saying D should be singular. And okay, I will focus on the case where Y is a surface. We will do everything when Y is a surface. Such pairs, commonly when Y is smooth, they're called low Calabi-Yau surfaces. We generalized the notion a little bit and allowed YD to have canonical singularities, but as canonical, we called such pairs low Calabi-Yau surfaces. And in this situation, we studied the KSBA moduli space for such surfaces. So typically, to obtain such surfaces, you can start with a toric variety, like we did, and do some non-toric blow-ups. So you can blow up on the smooth locus of D, and you will get a non-toric variety. Or the second way to obtain such pairs is to destroy the toric boundary, so you can smooth the toric boundary and no more have a toric structure. And what we did is to look at this moduli space MYDL, again, which is the closure of all stable pairs. I again fix the data of an ample line model on Y, L ample. Deformation equivalent to Y, I again fix D plus epsilon C as my divisor, where again epsilon is a small number and again C is a curve in the linear system of L. Okay, so I should have mentioned that already in the toric situation you might wonder, when I look at all such curves, when I had the toric situation, I know that the space of sections will give you a projective variety. You can think it's automatic. But the non-trivial thing is, if you look at the space of sections, even in the toric situation, the curves would have not necessarily SLC singularities. So the SLC condition is making things non-trivial. So here, it was a conjecture that in this situation, if I go beyond toric geometry, this moduli space should still be toric, and this is the main result. So okay, so Keel conjectured it around 2012, and it was concretely written on the paper of Hacking, Keel, and Yu. And we proved it with Alexeev and Bousseau. That MYDL is almost a toric variety up to passing to a finite cover. Is sometimes you need to take a finite cover, finite quotient of a toric variety, and we concretely described the fun with fun, the Mori fun of some x, and the main point, one of the subtle points is to tell you, if you don't have toric geometry, what is this x? And we gave a construction of this x, which we call semi-stable mirror. To YDL. Okay, so I will give you an outline of how this works in the remaining 5-10 minutes. 5, 6, 5, okay. So, okay. So let me tell you the steps of the proof. Okay, proof. So we start with YDL. And we consider all these maximal degenerations of YDL in the KSBA moduli space. And the step 1 of the proof is to construct this mirror X, semi-stable mirror X. And our construction is based on deformation theory. We construct it as a Crépont resolution of an affine threefold with canonical singularities. And this will be over a one-dimensional family. So to construct this, it was early on work of Kollár to ask when can you have such spaces if they arise as smoothings of some surfaces. You need to. So to construct this, we constructed a normal crossing surface with SLC singularities, actually Q-Goranstein singularities, and then obtained is that a smoothing of that normal crossing surface. And to construct the surface, we again used the generalization of what the toric momentum polytope is. So there's a Symington polytope associated to this data, and we viewed the Symington polytope as the intersection complex of some normal crossing surface with nice singularities, and then we showed we can smooth it. So this mirror construction is step 1, and as step 2, we looked at the double mirror. And we get a family over the toric variety, which I denote by m-sec. Toric variety whose momentum toric varieties with fan, the Mori fan of X. And because X admits such a nice Crépont resolution minimal model program, people will tell that it's a Mori dream space, so you can talk of its Mori fan of X. So we applied this we ran this double mirror construction, and then we showed that this is a family of KSBA stable pairs, which is a general fiber, includes the original YDL which we started with. So step 3, which is a theorem the double mirror is a family of KSBA stable pairs, which is the hardest part to show it as SLC singularities, the general fiber. Pairs, the general fiber, deformation equivalent to YDL. And this showed that the base parameterizing this family by the universal property of KSBA moduli spaces has a map to the KSBA moduli space, and we finally, in the step 4, showed that this map to the KSBA moduli space is finite and surjective. And this concluded the proof. I think that's all I wanted to tell you about. Thank you very much for your attention.
Question before lunch?
So the X bar you construct here is what you call semi-stable mirror.
Right. So we call X the semi-stable mirror.
Okay.
So we first constructed, associated to this data, we first constructed X0, a normal crossing surface with SLC singularities, and then we showed that you can smooth it. We used, okay, here all technical tools coming from log geometry came up. We showed that you can smooth it to X, and it's semi-stable as the central fiber sits inside as a normal crossing surface and the total space is smooth. And we used here log deformation theory, and because in this situation, whenever we have this, we know how to apply easier Gros-Sieber type mirror symmetry, and we showed that this contraction exists to claim that X is a Mori dream space, so we can make sense of the Mori fan. Okay. So we showed you can contract all curves and all compact curves to get. We studied the singularities of this construction to conclude this is a Mori dream space, so that we can make sense of the Mori fan.
Okay, I see. So X is not in general toric, right?
It's not toric. It's a Crepont resolution of an affine threefold with canonical singularities. It's non-toric general. Unless you start with something toric, you will not get anything toric.
Okay, okay.
Sure.
Other questions? Is there an interpretation of the fibers of your map of step 4?
That's a very good question. In our paper, we have not understood concretely the fibers of this map, therefore we proved step 4 in a very indirect way. So an earlier result of Sean Keel and you was saying that you will get a finite map from a toric variety to the space as long as you ensure, if you restrict it to one-dimensional strata, your family is not constant. And we analyzed this mirror construction to show that that property is satisfied. At the time we wrote this paper, we didn't understand concretely the fibers, what this map is really doing. But currently we are hoping to write another paper because we have a better understanding now what this map should be, explaining what this map is doing. But in our paper, we had a very indirect proof. That's a good question.
Hi, is the conjecture also for log Calabi-Yau pairs? Like are you using the fact that there's a toric model?
That's a very good question. The conjecture is at any dimension. We proved only in dimension 2. That's true.
Okay. So you are using that there is a toric model for the log Calabi-Yau surface?
We are using the fact that there's a toric model, but the more subtle point is here to run step 2, we do like Gros-Sieber type mirror symmetry. Sure. And this is step 1 is a R mirror construction, and going back is Gros-Sieber, and this is more concrete. But to make it work, you need to ensure the total space is smooth and you have a semi-stable family. And we know that in higher dimensions, even if we start with some variety with a toric model, we know that this is not going to be smooth. So even if we run our construction in higher dimension, we cannot go back. So that's the main technical point why we didn't do in higher dimensions. In dimension 2, we can ensure that the smoothing, log smoothing exists.
Another question? So if not, we thank you again.